Good afternoon, everybody. We are going to start on time, just so that we can be even close to finishing on time, but we are expecting people to come a little late. But Ross tells me he's used to students just sort of dribbling in, so it's not going to worry him. So thank you very much for coming to the last event in the extravaganza that has been 25 in 25, a celebration of teaching biotechnology at UQ. And of course, we have saved the best to last. On behalf of the university and everybody here, I'd like to acknowledge the traditional owners of the magnificent land that UQ has the privilege of operating on. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connection to country. And of course, we recognise the incredible contribution that the planet's oldest continuous civilisation has made to both Australian and global society. I have been asked to keep my introduction short, which I will do, because the man who is about to take the podium needs no introduction whatsoever. So I am simply going to ask you all to join me in welcoming the one and only Ross Barnard.
I feel like I need to get the guitar out after that introduction.
Feel free.
Thank you for the introduction, Joe. Thank you for doing the acknowledgement of the traditional custodians of the land. Good afternoon, everyone. Thanks for coming along. This is my first lecture to a live audience for 6 years, so please forgive my hesitancy at times. The last one was in April 2019 when I spoke to a group of chemical engineers. So it feels very strange being referred to as an icon. It should be obvious that at my stage of life I'm more in need of a hat than a halo. So since you all know me as wearing my cap, I'm going to put it back on just to keep my head warm. So 25 years is a long enough period, but I started with the biotech program in the year of the Olympics in Sydney, but in fact I first started work at UQ in 1982, and I'll get to that later. It's a great pleasure to be surrounded by so many remembered faces. You're all formally trained in biotech. You've built careers, very distinguished careers in that field, so it's difficult for me to tell you something you don't know. So this can't be a routine research seminar. It's going to be, that would be too narrow in its scope. So I'm going to take you off in some unexpected directions and perhaps jog some memories in the process, and at least it'll be a chance for me to speak with you all again. And I'll probably take questions afterwards over drinks rather than immediately after the talk. I think for the content that would probably be more appropriate. So I've been very privileged to work with many wonderful, talented and hard-working students. That's one of my lab groups back in 2010, and then a group of exchange students who went to the University of California, and Stephen is here tonight, one of the exchange students. And there are many elements to a career in biotechnology. This is one of my paintings that captures some of the elements and compounds that I've worked with over a period of 45 years. And I'm delighted that James has seen fit to hang this in the boardroom in the School of Chemistry and Molecular Biosciences. So on the top left of that image, you can see glutamate and there's magnesium. And both of those I'll speak about later on in this lecture. So science as process is the theme, but it will have an educational orientation since I was in charge of the teaching program, so there'll be some insights into teaching and learning along the track. So today I'll talk about science as process. Our tools are a catalyst for that process. These images both depict a microscope constructed by the pioneer lens maker Antony van Leeuwenhoek in the 1660s. It was only a few centimetres long with a very short focal length. But the droplet was actually placed there and acted as a second lens, producing greater clarity and magnification than the contemporary compound microscopes that suffered a lot from aberration and weren't very good. And it facilitated the first observations of protozoa and bacteria. So, I'm not sure about the average age of the audience, but not all of you will remember Professor Julius Sumner Miller, but I watched his lectures with great enjoyment on black and white television back in the 1960s, and he always opened up with the catchphrase, "Why is it so?" And most of our science begins with the question, "Why is it so?" This is Elizabeth Blackburn. She won the Nobel Prize for her work on telomeres. She had this to say about the education of scientists. So it all depends on the quality of the thinking, and that is where training is much more important and the subject matter less important. Teaching people the best scientific thinking is much more important than making sure that they have all the facts about something, because frankly, the facts change. So this statement by Elizabeth Blackburn has a remarkable resonance with the ideas of John Dewey, the famous philosopher and educator, and he had this to say about thinking. Thinking is the power of following up and linking together the specific suggestions that specific things arouse. Accordingly, any subject, from Greek to cooking, drawing to mathematics, is intellectual, if intellectual at all, not in its fixed inner structure, but in its function to start and direct significant inquiry and reflection. So this is the key to why artificial intelligence is bad for learning. Because AI might be okay for plausible, albeit superficial, non-critical summaries, but it's a barrier to student engagement precisely because it usurps the work of linking together. That's the key point. So for that reason, I assert that AI is anti-Deweyan, at least in some applications. For some things like molecular modelling, 3D modelling and AlphaFold and that stuff, it's fantastic, but not if you actually want to engage with the material in a meaningful way and link concepts together from what would be disparate areas of knowledge. So, science is neither a collection of facts nor the fixed inner structure of a discipline. It's a process carried out by both individuals and communities of scientists. Now, in his book, Creativity in Science, which is a brilliant book, Chance, Genius and Zeitgeist, Dean Simonton from UC Davis emphasised that even so-called lone geniuses emerge from a conducive zeitgeist. And in the words of Niels Bohr, we are both actors and spectators. So we are actively entangled with the phenomenon that we observe, not only in theoretical physics, but in any field of science, our choices of observational method will reveal different, sometimes complementary aspects of the observed. Of course, what is critical to the scientific process is that different observers using the same observational apparatus can replicate the results. So if you want to learn more about entanglement between observer and the observed and complementarity, I direct you to this paper that I published in 2023. And I'm going to provide the references for this talk afterwards, so if you want to get the references, you'll be able to obtain them. So back in 1999, just before I came back to UQ to work with the biotech program, Peter Wills came up with this idea of a virtuous cycle between the universities and industry, and he called it the virtuous cycle. Now, it's not necessarily virtuous, but it's absolutely necessary for both the universities and industry. This cycle is mirrored by a second. My students have all seen this. It's in my Intro to Biotech lectures. The key message is that science and technology are intimately related to each other in a positive feedback loop, but they are not identical. Unfortunately, in much of the media and social sciences, science and technology are frequently conflated, leading to all sorts of confusion. This has also, some sociologists have made the spurious suggestion that indigenous cultures did not do science, where evidence showed that this is false. It might be true that the technologies are different, but the process, the core process is the same, and I'll get back to that in a minute. So from this clear differentiation between science and technology arises the definition of biotechnology. Indeed, all of my students have seen this definition, but the reason I'm putting it up is to point out the use of the future tense. And this will come up later. The products of science might be and are frequently way ahead of what the community values, understands or believes. So this is a signpost in the Mount Cootha Botanic Gardens. I'll just give just 3 examples of biotechnology before I launch into the body of my talk. So the first is this one. This is in the Mount Cootha Botanic Gardens. It describes the use of the foam bark tree by Indigenous people, the use of the bark to poison fish, and the discovery that the fish remain edible could only have been discovered by a repeated empirical process involving careful observation and testing, both key elements in science as process. Second example is a modern example of the application of biological knowledge combined with physics. I have 2 intraocular implants inside my eyeballs, 2 methacrylate Zeiss lenses, thanks to my brilliant eye surgeon Mark Lone, who is also a University of Queensland alumnus. And third example is this. Now, we have the biological knowledge that humans with illnesses, particularly metabolic disorders, release characteristic odorous chemicals. So dogs can be trained to detect those chemicals and alert the owner to take their medication. This is actually my son's medical assistance dog, Ben, trained at the University of Veterinary Medicine in Vienna. And he's simply amazing. So, keeps him alive. So, science is process. So, the models we create are provisional. Perhaps this is what differentiates modern science from ancient science. It's the dependence of modern science on models. To talk about science as process, we must talk about models. It might be a shock to those coming out of the secondary science education system to know that our models are provisional, although in many cases we do end up having a great deal of confidence in them. So I'll begin by talking about plastic models, solid ones, before I launch into the metaphorical. So I think some of the audience here are old enough to remember them, not looking at anyone in particular. The CPK models were developed in 1953 and was still in use in the 1980s when I was doing my PhD. This model was constructed by me and my colleague Scott Rowlandson in the late 80s. So these things were beautifully engineered, precision engineered. Here you can see the models of carbon and oxygen with various valencies and the requisite bond angles. Beautiful things. And they were assembled using a spanner, so they were tactile, rotatable, mechanical. They could not be more different from computer-generated images. Nevertheless, they were superb for the study of stereoisomers and for the secondary structure of proteins, including hydrogen bonds, and not least because you could wrap your hands around them and really get a good feel for what the secondary structure meant. Now I'll get into some real science. Some serious science. From 1982, I was working on the binding of growth hormone to its cognate receptor. Is it there, the GH receptor, even though at the time we didn't know the structure. That came from our later work. So in those days, so I was studying the binding of growth hormone to the GH receptor. In those days, we didn't use surface plasmon resonance to measure affinity constants. Instead, we used a clunky method called Scatchard analysis with radioactive labelled growth hormone. And a steeper gradient on these graphs indicates a higher affinity, a lower gradient indicates a lower affinity. What I found that when I added calcium or magnesium ions to the binding mix, the human growth hormone bound with a 19-fold higher affinity, equivalent to a energy equivalent to a 7.3 kilojoule per mole difference in the binding energy. By contrast, the same divalent cations had a slightly inhibitory effect on the binding of non-primate growth hormones. So our hypothesis was that the positively charged calcium ion was neutralising a critical negative charge on the surface of the growth hormone receptor, a negative charge that was not present in the non-primate hormones. And fortunately for us, Charles Nicholl had recently published sequence alignments for a big family of growth hormones. We compared all of these sequences and we discovered that there was only one hormone in the whole bunch that had a negative charge at position 33, and that was human growth hormone. So we postulated that this unique negative charge was the one that could account for the unique calcium or magnesium ion dependence of human growth hormone binding to its receptor. So we came up with this first of our non-physical models. This simple, indeed naive model could account for the energetics of the interaction with the divalent cation here between the human growth hormone and the receptor, and the non-requirement for a divalent cation with the non-primate, where you had a positive charge there to interact with the negative on the receptor. So the problem with this model was it required a divalent cation to float in between receptor and hormone. So this was unlikely to be a stable system, so it was an unlikely model. So it made more sense if the calcium or magnesium ion was chelated to the surface of the GH molecule. So I built this model of the carboxy terminus of helix 1 of growth hormone and found a nice chelation site. I really don't need to point, you can see it there. And note the magnesium ion was a homemade rolled up ball of aluminium foil. So the model of growth hormone built in mid-86 was already something of a relic by the time this article came out in UQ News, because the Silicon Graphics computer modelling software had recently arrived at UQ with Peter Andrews and the drug design unit, along with scientists such as Luke Goddard, Jenny Martin, Paul Aylward and Ross Brinkworth. And the image on the right is an analogue photograph glued into my PhD thesis. Now, this is how the model was rendered for publication in the Journal of Theoretical Biology. This was hand-drawn. It was traced from the photograph, then outlined and shaded with ink. And we all had to do this sort of stuff. We had to draw our own diagrams. It's just great training in a way, but incredibly laborious. So this was the second model we came up with, which is a sort of geometric electrostatic model. And note that the postulated negative charge on the receptor, two negatives with the chelated calcium ion in the human complex, in the absence of the cation here, and then down the bottom the non-primate complex that doesn't require a divalent cation. So then, using Coulomb's law with a distance-dependent dielectric function that was provided by Brian Hingerty at the Oak Ridge Laboratory, who assured me that it was okay to use classical rather than quantum calculations for distances greater than 4 angstrom. And with advice from Bert Frost in the physics department, I made calculations that yielded testable predictions of the intermolecular distance. Note here that I had to rely on advice from the physics authorities when I was doing my PhD, and I'll get back to that. So we published our model on the cover of the Journal of Theoretical Biology, and we predicted these distances between a negative charge on the receptor and these charges on the surface of the hormone molecule. And then, whoops, wrong way. Then a few years later, we had the X-ray crystallography images, which enabled us to test our model against reality, and it eventuated that the distance we had predicted between the charge centres of glutamate 33 on the hormone and a protruding negative charge on the receptor, the distance was actually 7 angstrom, which was remarkably close to what we'd predicted using the classical Coulombic calculations. But as my dear supervisor said at the time, Mike, he said, "You're probably right for all the wrong reasons." So he was typical encouraging statements from one's advisor. But the actual distance was 7. So we then proceeded to test this model further by doing charge reversal site-directed mutagenesis, because we made the testable hypothesis that we should be able to convert a human hormone into a non-human hormone by making a single charge reversal mutation, which we did. Or I should say Scott, by that time I'd gone to the US, but Scott kept working and he did that charge reversal and showed that that was true. We could convert the primate to the non-primate hormone just with that single charge reversal. So there's me on the right nursing either helix 1 or helix 4, I can't quite remember which it was, and Scott on the left with an acceptance letter from the journal Biochemistry, and Mike there holding the cricket bat. So I then, this was prior to the availability of the crystallography images, I had boldly ventured on where no one had ventured before and built these highly conjectural models of the complex between GH and GH receptor, which turned out, perhaps unsurprisingly, to be wrong. So although we had because I didn't have any data to support that, it was just a complete conjecture. So although we had successfully predicted the location of critical interactive charges and some key distances, the detail of the multiple interactions in the complex was only revealed later by X-ray crystallography. So Werner Heisenberg was uncertain about many things, including his politics, but he was very precise in relation to models. The models might have great internal consistency and we can develop a great deal of confidence in them, but experiment is the ultimate arbiter. So we scientists create models and hypothesize based on these models using our right brain, ostensibly our right brain. We create systematic experimental designs to test those hypotheses using ostensibly our left brain. So science is both an intensely creative and a rigorous process which uses the entire brain. In relation to the red writing there, neuroscientists have in fact shown that the idea of a left brain, right brain schism is in itself a gross simplification. But it's a nice story. So Karl Popper was a Viennese philosopher. Again, we're back to Vienna. He fled Vienna in 1937. He was a great proponent of the idea of falsifiability as the key feature that distinguishes science from non-scientific statements. Okay, he was also a proponent of the idea of conjecture and refutation. In fact, Popper was refining a principle that had been implied more than 300 years earlier by such scientists as William Gilbert in his book De Magnete, where he said this: "Many things in our reasonings and our hypotheses will perhaps seem hard to accept, being at variance with general opinion, but I have no doubt that hereafter they will win authoritativeness from the demonstrations themselves. In other words, if general opinion disagrees with experiment, then general opinion is wrong." Note that he said, "I have no doubt." So he was an optimist, and like Galileo, he had faith in the transcendent value of experimental evidence for convincing people of the truth. Wow, wouldn't he be disillusioned if he lived today? So in Galileo's case, such faith was unfounded. But I especially note Gilbert's disdain for general opinion or consensus. So experimental evidence connects our models with reality. Why was Popper motivated to clarify and remind the world of the principle of falsifiability? The answer: these principles seem to have been forgotten. Popper had escaped from a Europe torn apart by ostensibly infallible political ideologies. So our models are provisional. If the models don't agree with the experiment, we throw them out, modify them, or in the best case, the model becomes subsumed as a special case into a more general one. So unlike political dogma, probably the best known examples are the Bohr model of the atom, subsumed as a special case into orbital theory, and Newtonian physics, subsumed as a special case into general relativity. So a corollary of the Popperian view is that if science is to progress, scientists must be free to be wrong. But it's important to note that in practice, falsifiability is imperfect because our knowledge of complex systems is frequently incomplete. One could argue it's always incomplete. Now, this is going to sound like Sir Humphrey Appleby in Yes Minister, but I'm going to read it anyhow. So, testing a hypothesis H involves deriving from it an observable consequence O, but in practice O may also depend on other assumptions or unknown conditions A. So if H appears false, it may be that O is false, but it might also be true that O is false and O is true and A is false. So it might be a good strategy to hang on to an hypothesis even when an observation seems to imply that it is false. So this also proves that there's more to science than falsifiability. So correct theories can on occasion be falsely discredited. And the weird thing is that the reward system in our scientific institutions is such that it's much better to prove a theory right than to prove it wrong. So our reward system is actually at odds with the Popperian view of how science happens. So in 1951, Hannah Arendt said this: lack of availability of truthful information can be at least as damaging. So the quote from Hannah Arendt immediately prompts the demand, tell me what is true, especially in a world where we are immersed in fake news, my truth, alternative facts, my narrative, repetition and opinion. So tell me what is true and what's an illusion. So you will recall that the 17th century scientist William Gilbert had a disdain for what most people think. What most people think can be a big problem, especially when they're not actually thinking. So the Chamberlain family, I thought I'd have a whole lot of really young people here who wouldn't have heard of this story, but I think I'm sorry. But they were camped at Uluru in 1980. A dingo entered their tent, took and killed their baby, and the plaintive cry, the dingo's got my baby, entered Australian folklore. So there was mass prejudice, herd mentality. Lindy was not believed. On the contrary, she was blamed, a pattern that is all too familiar today. So evidence from the local Indigenous people was ignored. Forensic evidence was misinterpreted. So the investigators, forensic investigators, initially found bloodstains, in inverted commas, in the family car, and the court concluded that Lindy had taken the baby to cut her throat in the car. Later analysis showed that the stains came from a spilled drink and the sound deadening spray used to manufacture the vehicle. So Lindy was released from jail in 1988. She was there for 6 years after new evidence of the baby clothes turned up. And finally, in 2012, the coroner in the Northern Territory finally ruled that the baby had been taken by a dingo. So what most people think is also a driver of the stock market. This is the stock price for the A2 Milk Company, which was listed on the ASX back in 2015. In 2025, the price of a share was still 939% of its price at listing. Now, I'm going to quote an article by Nick Fuller, who is a fellow in clinical trials development and analysis at the University of Sydney. Here, Nick is acting as what I refer to as a knowledge gatekeeper. So he said this: for those who do not experience any problems with milk consumption, there is no evidence to suggest any benefit in having A2 milk over the common consumed commercial milk, which contains both the A1 and A2 proteins. For less than half the price, the latter would be the favoured option. So fad science is related to and intersects with fake science in that it is sustained by fashion, publicity, and not by evidence. Unfortunately, it can really take off despite the efforts of gatekeepers. So these are sometimes political stunts. They can have dangerous consequences, for example, pronouncements on the effectiveness of ivermectin as a COVID therapy before clinical trials, recommending high-dose vitamin A instead of vaccination against measles. So gluten, the gluten-free fad. I'm sure there's lots of gluten-free food going to be available after this talk. So people with celiac disease have severe immune reactions triggered by gluten. About 1% of the population actually has celiac disease, and a gluten-free diet is essential to eliminate the inflammation. However, why is it that between 20 and 30% of the population, this is in the US, so maybe we're not quite as batty, but 20 to 30% of the population in the US follow a gluten-free diet. So Robert Schmerling from the Harvard Medical School gave a summary of the drivers of this fad. So intuition, The inflammation connection, so the idea that because gluten triggers inflammation in people with celiac disease, maybe avoiding it will reduce inflammation in me, though there's actually no evidence supporting this for people without celiac disease. The usual culprits, celebrity endorsement, anecdotes and marketing. So cognitive scientists have found in systematic peer-reviewed studies that repetition leads to something they call illusory truth. In plain language, if you repeat a lie often enough, people will believe it. So the principal weapon of politicians. So do we need knowledge gatekeepers to enable competent outsiders to evaluate information? Well, yes, we need them for all of these. I've given you 2 examples of where we need them. There's a whole range of reasons why we do need them: to minimise risk to public health, to filter the mass of information, to counter bogus claims, to enable safety in our research and medical practice, and to counter politically, economically motivated untruths. So in many countries we have committees whose members are vested with authority based on their extensive experience in particular fields of science. So, for example, what's happened here? Let's go, there we are. So, for example, in Australia we have these committees and others. The professional societies also take a significant role in public education and, of course, on issues such as vaccine hesitancy. And, of course, we have trusted institutions like CSIRO. So, do we need knowledge gatekeepers? In 2022, in the wake of the COVID epidemic and the ongoing proliferation of misinformation, Osborne and Pimentel in the journal Science suggested the need for gatekeepers in a much broader sense than the narrow one required for civil administration. They published a heuristic or decision tree to help so-called competent outsiders evaluate scientific information. So the key steps, you can see the top one, number 1, is the source of information credible? Does the source have the expertise to vouch for the claim, with an emphasis on the reputation among peers? And then item 3, is there consensus among relevant scientific experts? And if not, what do the most highly regarded experts think? Okay? Now, this is not simple. So this has a very noble intent and is potentially very helpful to teachers and other members of the public, but teachers should be mindful that firstly we are talking about islands of temporary stability of knowledge, not a collection of immutable facts that's carved in stone. So I introduced you to this heuristic that Osborne and Pimentel introduced in 2022 and talked about the fact that there were some issues with that because you need to be mindful that we're talking about temporary islands of stability of knowledge, not immutable facts. And there's an assumption of an alignment between truth and consensus, which ain't necessarily so. And the heuristic also defaults at point 3 to what do the most highly regarded experts think. Now, this raises the crucial question about who decides who are to be presented to the public as the most highly regarded experts. Is it the news media, social media influencers, the government of the day, or scientific peers? Now, history, even recent history, shows that this can too easily slide into a question of media profile or power relationships. Or, as was stated way back in the 1st century CE by Juvenal, quis custodiet ipsos custodes, which you all know means who will guard the guards themselves. So Osborne and Pimentel heuristic is based largely on authority, and in an ideal world, authority should be derived from specialisation, track record and skill, and not from political power. Deferring to it can have important practical rationales. Just as in my PhD, I needed to rely on the authority of 2 physicists to get tacit, non-codified knowledge about carrying out or interpreting complex experimental or analytical procedures. So, however, teaching people to whom they should listen or what to think is not the same as teaching critical thinking. Indeed, there are ongoing discussions in the scholarship of education community in Australia as to whether critical thinking can be taught or how it can be taught. So formulation of falsifiable hypotheses and experimental design could be considered parts of a process of critical thinking, and indeed they are so considered in the current National Core Concepts project for biochemistry and molecular biology, coordinated by Amber Willems-Jones at Melbourne. So the heuristic is well-meaning with a very noble objective of helping competent outsiders evaluate scientific information. Then, unfortunately, they went and spoiled it all by saying this: in most cases, dissenting voices turn out to be wrong. Okay? Being wrong is part of the scientific process, as I've shown, and moreover, history shows that paradigm-changing breakthroughs invariably come from dissenting voices. History also shows that gatekeepers of knowledge have been notoriously bad at distinguishing between wrong ideas and breakthroughs. So we need to look to Thomas Kuhn to understand that. So there is more to science than falsification, but the Kuhnian and Popperian views are not incompatible. Kuhn's view is that science proceeds gradually, but with intermittent radical shifts. So one way of representing Kuhn's view of this, so this is 2 time points. On the left, time point 1 and time point 2, and we see 2 distributions of ideas. At time point 1, you've got this bunch of ideas out here that are outside the boundaries set by the gatekeepers. But at time point 2, a subset of these ideas will then become the norm and no longer out of bounds. So outliers are defined by the characteristic that they meet resistance both within and outside the scientific community. Disruptive advances are by definition outliers. Now, Eric Skerry got it right when he said this: numerous instances from the history of science show that progress is achieved by violating what may have seemed to be inviolable restrictions. And Eric is at the UCLA Chemistry Department. He's the founding editor-in-chief of the journal Foundations in Chemistry. So he has authority. So I'll now launch into some case studies. So accelerated stability testing. I think enough of the audience here would have encountered and be familiar with that. It's a process undertaken frequently in the diagnostics, pharmaceutical and textile industries. It allows us to work out the shelf life of a drug or diagnostic kit much more quickly than otherwise by measuring stability at high temperature, then using the equation to extrapolate stability at the real-life storage temperature. To do this, we assume that transition state theory applies to the entire assemblage of chemical degradation reactions in a kit or a formulation. In effect, we are treating the entire assemblage as a single component. So there it is. So if you plug, say, the accelerated temperature at 52 and the room temperature or real-time temperature at 22 degrees, you can see that the real-time shelf life would be about 8 times longer than the accelerated shelf life. So what is the theoretical basis for this equation? I know my former PhD student would say it comes from the Arrhenius equation, 1889. Generally, it's said to be derived from Arrhenius, which relates the rate constant K to the temperature of the reaction. This was an empirically derived, principles-based model. But in fact, Arrhenius has a theoretical foundation in and can be derived from the earlier and broader work of Ludwig Boltzmann, 1877 or earlier. So the physical chemists will know all of this stuff, but the partition of molecules within an energy distribution can be expressed using Boltzmann's distribution law, equation 1. And as T is increased, more molecules will have energy exceeding the activation energy of transition state and the reaction will proceed faster. The form of equation 1 can be readily transformed into the form of equation 2, which is the accelerated stability approximation. So last time I was in Vienna, back to Vienna again, 2019, I took the 71 tram to the Central Cemetery to visit the grave of Ludwig Boltzmann. And there at top right, you can see the entropy equation on his gravestone, S equals K log W, Boltzmann was a brilliant scientist who had a sad life. So Boltzmann developed the theory of statistical mechanics, developed the concept of entropy, S equals KLNW. That's not a minus sign, that's the PowerPoint dash, sorry, S equals KLNW. The constant K is now known as Boltzmann's constant. It was originally expressed as the gas constant divided by Avogadro's number, but Max Planck introduced the small k later on. So these ideas were ardently opposed by his contemporaries Mach and Wilhelm Ostwald, who didn't believe in atoms. From 1904, even the young Einstein was sceptical about S equals KLNW. So these people occupied powerful positions as gatekeepers and silenced Boltzmann's ideas. He was convinced that his theory was fundamental. He didn't receive any support. It was disregarded by the Royal Society, and he committed suicide in Italy in September 1906, just a matter of weeks before his ideas started to take off and gain acceptance. So I used to tell my students, if you're feeling depressed, just wait a few weeks. So Boltzmann, he didn't live to witness the acceptance of his ideas. Then in 1905, Einstein had a change of mind and described Brownian motion mathematically based on a model of atomic collisions. And it turned out that Planck needed Boltzmann's energy distribution equations for his work on blackbody radiation. But unfortunately, the scientific community is much less interconnected. Information diffused very slowly, and Boltzmann was living in a villa down in Italy, near Trieste. It was a bit out of the loop, unfortunately. Next one, Ignaz Semmelweis. The microbiologists will know this one, but I'm leading somewhere else with this. So Ignaz Semmelweis introduced hand disinfection standards in 1847. There was a dramatic reduction in mortality from postpartum infection. He was a pioneer in using health statistics. His observations conflicted with established scientific and medical opinion. The obstetricians at Pest never adopted his methods, partly because there was no theoretical explanation. This was decades before Koch, Pasteur and Lister. But the doctors were arrogant. They even ignored the evidence of the statistics, that one ward had very low deaths and the other one had so they basically ignored the data. They rejected his suggestion that they should wash their hands. In 1865, Semmelweis was committed by his colleagues and his wife, bear that in mind, to an asylum. In the asylum, I'm not sure what the message is there. In the asylum, he was beaten by guards. He died 14 days later from gangrene, and his practice was not accepted until decades later after the work of Pasteur, Koch and Lister. So the trait of human behaviour characterised by automatic rejection of new knowledge because it contradicts entrenched norms, beliefs or paradigms has been called the Semmelweis reflex. Now, it's often seen as an old problem, but it's not. So, as illustrated by the delayed recognition of airborne transmission of COVID-19. So, despite evidence, early evidence indicating that there was aerosol spread, the focus of WHO was primarily on droplet transmission. So it was not until December 2021 that WHO officially recognised airborne transmission. So integrating innovative perspectives swiftly in existing frameworks is a significant challenge. And what the WHO says is normally based on a consensus of expert advice and opinion. And this is a paper by Dayani published in Nature, so it's in a reputable journal. So this is just a small selection of ideas that were resisted by knowledge gatekeepers. I've highlighted the Australians in purple, Warren and Marshall, who work on Helicobacter. And I've also highlighted the one on chromatographic adsorption analysis of chlorophylls by Tsvet, because there's been an excellent paper published on the reasons for the rejection of chromatography. So overlaid on this sort of resistance is political resistance. For example, in Europe, resistance to golden rice, the brilliant innovation by Ingo Potricus, which actually prevented access to this technology by developing nations in Africa. So let me see. So sometimes we find ourselves in an unfortunate situation where the politicians are the gatekeepers, and that's a big problem. So it's supposed to change. Let's see. Technical, can you get me over there? Oh, yeah, I've got to go back over there. That's it, thank you. There's the paper by Jonathan Livengood on Sweat's chromatographic absorption analysis. It's well worth a read. Okay, the next case. So case study 3 is Trofim Lysenko. I'm not sure any plant biologists, geneticists here tonight. I can't see Pierre. He rejected Mendelian genetics. This is in the, as late as the 1950s. His work on crop adaptation invoked Lamarckism. His ideas aligned with the political ideology of the Soviet government, and they were promoted and became state-sanctioned doctrine. So in 1940, he was promoted to director of the Institute of Genetics of the Soviet Academy, and with state support, he suppressed dissenting opinions, discredited and marginalised his critics. Scientists who refused to renounce Mendelian genetics were dismissed, hundreds were imprisoned, several were sentenced to death, including the world-famous geneticist Nikolai Vavilov, who died in prison in 1943. And Lysenko's ideas were exported to China and were catastrophic. So recently in Russia and China, there have been pushes towards rehabilitating the ideas of Lysenko with recourse to epigenetics. And an excellent refutation of this is an article which comes from Russia and Germany by Kolchinsky and colleagues. And their summary is basically the research in the model plant Arabidopsis shows that it's clear that Lysenkoism has nothing to do with heritable epigenetic modifications. It's just a method of inserting ideology into scientific discussion, and biologists should defend science against ideological and political interference. So my last case study is this one. Is that so this reinvigoration of Lysenko coincides with some sort of nostalgia for Stalin in Russia at the moment. So my last one, so political interference is widespread, and we've seen particularly egregious examples in the administration of science in the United States at the moment. But I'll show you this in case study 4. If you consider the Italian National Agency for New Technologies, ENIA, eminent scientists within the department could be promoted to directors. In the Italian system that then existed, promotions were based on political affiliation rather than scientific accomplishment. So for every 2, you had the ridiculous situation that with every 2 Christian Democrats promoted, you had a socialist, a communist, and someone from a smaller party would be named as dirigente, I guess something like the Australian Senate. So eminent scientists were not promoted because they refused to join a political party. So in my conclusions, I'm not doing too bad seeing we had the bit of an interruption. Experimental data connects our model making and conjectures with reality. Experimental data cuts the Gordian knot of the question, what is true? It differentiates science from non-science, fad science from real science, and science from politics. The concept of knowledge gatekeepers is a two-edged sword because consensus can be fallible, it can slide into groupthink. The concept of gatekeepers can create the impression that science is a bag of content rather than a process. At least the peer review process, we can hope, should be insulated from political and ideological interference, even if it is hopelessly unrealistic to expect the ministerial sign-off on research grants or even academic promotions to be free of political interference. So again, John Dewey hit the nail on the head. Back in 1938, he said, in scientific inquiry, the criterion of what is taken to be settled or to be knowledge is being so settled that it is available as a resource in further inquiry, not being so settled as to not be subject to revision in further inquiry. So here he's talking about those temporary islands of knowledge stability. So science is a process along paths marked out by islands of temporary knowledge stability, not a collection of immutable facts. Paradigm-changing science generally meets resistance or is rejected, contrary to the implication of Osborne and Pimentel. paradigm-changing science is frequently not safe for the scientist. So my biotech students might remember this. How many remember this movie? Yes, I forced a lot of my students to sit through this 1951 movie, Man in the White Suit, in the introduction to biotech courses. So the work of Sydney, the brilliant, driven textile scientist, had unexpected consequences and was certainly not free of risk for those around him. So paradigm-changing work can have unexpected consequences and raise significant ethical questions. So this is the essence of science as a process. It's pretty simple. So if someone says it's raining and another person says it's dry, it's not your job to quote them both. It's not about balance, okay? It's your job to look out the window and find out which is true. And the way you are looking might be a synchrotron, might be a thermometer, might be a sequencing machine or a microscope. And it's very important to remember that it was Galileo's observations of the planets with the telescope, not his great discoveries in physics, that brought him into conflict with the intellectual establishment and the church, i.e. the gatekeepers of his time. Okay, I've managed to make up time, I think. Thank you very much. These are the people I must acknowledge for their input. And I will make all of this list of references available somehow after the talk. So thank you very much and sorry for the glitches.
Really can't. Good afternoon, everyone. My name's James DeVos. I'm the head of the School of Chemistry and Molecular Biosciences, where biotech sits. And I find myself in a terribly invidious position, standing between a Ross lecture and a free drink, and a beautiful location for you, so I'll at least try and be brief. Brenda asked me to thank Ross for his talk, but this morning I had a change of heart. I decided that I'd much rather do something else. And so with all...
well, don't thank me then.
So with all due deference to Shakespeare and Julius Caesar, I find myself that I've come to complain about Ross rather than to thank him. And so I knew this was going to be difficult when last night Brenda told me, rather fearfully I must say, that Ross had 300 slides for his 50-minute lecture.
105.
And she wondered how that was going to work. And I was transported back in time to, because I've been here before, to a lecture that Ross gave in TUM at the Technical University of Munich.
On climate change, right?
Yes,
yeah.
no, it was on. It was at the end of a bioeconomy meeting that was established. So trying to establish links between UQ and the Technical University of Munich. And as bioeconomy, for those of you who don't know, doesn't have a very good definition, and it's much more fuzzy even than biotechnology. So it can be anything, and that conference had lots of people talking, and so we had everything from hardcore organic synthesis to biochemistry, to using food waste as an energy source through fermentation, to solar cells and the materials that made them up. And so Ross's job at the end of this lecture was to summarise, to wrap up and summarise this. And the fearful conversation at breakfast that morning from the delegates from UQ was that we'd seen Ross's slide deck and it was several hundred slides long, so for his 30-minute talk. And so we were all terrified as to what was going to happen and whether TUM would ever talk to us again. Needless to say, it was a tour de force, and Ross managed to summarise thoughtfully and insightfully this completely unsummarisable lecture, and it was very good, and so we were all amazed. And it was at that time I realised that Ross was a polymath, And so I looked up the definition this morning because I thought I knew what it meant. And having just seen Ross's lecture, I think you'll agree, because a polymath is someone who has knowledge of many fields and uses that knowledge to solve problems, both concrete, specific problems and more abstract problems. And I think that Ross demonstrated well his thought processes in trying to do that. It was in fact a joke amongst many of his colleagues, he probably doesn't know that, where we were trying to figure out what exactly Ross was, because we were chemists or biochemists or microbiologists, and we would try and guess whether Ross was really a biochemist or a molecular biologist or a microbiologist or even a chemist. And as it turns out, I think he was just a polymath and was good at all of these things. And of course, like a polymath is often related to a Renaissance man, and that is the definition of someone who doesn't accept limits on their knowledge or on their ability and can develop not only their knowledge but their sort of artistic and sporting endeavours. And Ross is horribly just someone like that. I think the story I was told, I don't think it's quite true, it's maybe apocryphal, but it's close, that Ross retired from the University of Queensland firsts in AFL when he realised, I think he was twice the age of the next person
52.
behind him.
I was 52.
Yes, yes, or at least was old enough to be the father of everyone else in the team. He thought he'd have enough. He thought he'd had enough. And of course, you know, that's not the limit of Ross. Ross is fluent in Mandarin, because of course he's fluent in Mandarin. And he's
anymore.
also an artist, I think. Do we have?
Yeah, they've added one at the end, I think.
Can I
If you
actually
told me.
change the?
Yeah, this one should.
Okay.
There we are.
Oh, one more.
We'll get there.
One more.
One
yep.
more.
One more.
No, loves. You're using the wrong one.
No? We're getting there.
No.
Is it?
Sweetie, you were
Am
changing
I?
the laptop. This is...
Oh, yes.
Yeah, there we go. All right.
Okay.
So this is the
So much
painting
for polymath.
that we've hung in our in the conference room of SCMB, because not only is Ross, of course, an athlete, a scientist, and everything else, but he's also an artist, and this is just one of his paintings. And of course, everything it appeals to me, of course, because it's all chemistry and how his scientific career has been influenced. But of course, in case you missed it, not only did he paint the damn thing, but he published it. So there's a little reference down there. And then, of course, for the biochemist, molecular biologist, he published it in Clinical Chemistry. So, anyway.
And the blue glass on the bottom right is a replica of something done by Jared Wright from the glass blowing.
Yes, and so of course
facility.
Ross has gathered together a little artistic community within including one of my former students within SCMB. So I'm not going to thank you for the lecture, Ross, but as head of school, I will thank you for the unstinting energy and enthusiasm that you put into establishing biotechnology at the University of Queensland. It has really transformed SCMB, I think, from a largely undergraduate, postgraduate, research postgraduates, but largely undergraduate domestic students into a vibrant community that has a significant number of international postgraduate and undergraduate students, as well as our continuing domestic ones. And I don't think anyone else could have managed to do that. So for that, thank you. And if you like, you can thank him for that, or you can thank him for the lecture.
Thank you. Thank you. Thank you very much.